Yeah, although it's not me, I need to fix it. Anyway, yeah, so let me make sure the screen is getting projected. All right, okay. So, following off last week's lecture, I felt like Thursday's lecture was a little rough. And I thought about, just continuing with some transformer, just some, like adding in some more information. But I generally find that when your foundation is as shaky, then no matter what you add on top of it, it's still going to be shaky. It never ends well. So what I want to do is go over the transformer lecture again. But this time I want to basically restructure it a bit so that we have a good idea of what we're doing, what inference is, what tokenization is, all of that. Do some basic coding model, do some basic code snippets, look at that, and then run through how transformer attention works and all of that. So hopefully, you guys have seen a lot of this before. I added in a lot of new content, especially sort of examples that we could explore and we could talk about, and it'll probably go faster than last time, but hopefully going through this one more time will be beneficial. Honestly, beyond anything else, if you want to get in this field, the most important thing you have to understand is transformers. Most important thing you have to understand is intention. So from that standpoint, it's probably a good idea to just go over it again. Make sure our understanding is strong, right? So let's start off. Starting again, we left RNNs because RNNs are slow. Basically, you have to process data sequentially. This is true for both inference and classification or any other NLP task. You have to basically put in data one word at a time. That's not a great thing. You imagine if you had to put in an image, one pixel at a time, right? That was one of the examples in the actual RNN, an RNN paper, which was we put in the image one row at a time. That's not great. It's not ideal. We want to be able to put in a lot of data at once. Computing relies on parallelization. Then there's a vanishing or exploding gradient issue. Again, if we have a gradient is the function of multiple layers, and multiple layers will have gradients of either above or less than 1. And so if you combine those, you could get something that trends towards 0 if all the layers have a gradient that's less than 1, or something that explodes if all the layers have a gradient that's above 1, right? So that's what's known as a vanishing or exploding gradient problem. And then there's the lack of attention. Basically, an RNN processes each word in order and just looks at the word and has a hidden state to sort of have an idea of what came before it, but not necessarily has a strong idea of what came before it. It's basically going to treat everything that came before it equally. But we know the way we speak, that's not necessarily a good thing. For instance, as I'm speaking right now, you're sort of listening to me and you're learning, and you know that there are certain words that you're paying attention to. For instance, when I say paying attention, you know that those two words you're paying attention together, and there are certain words you're not paying attention to. Sort of stop words, the, a, something like that. Just words that sort of allow us to have a flow in the language, but not necessarily are super informative. That's the issue of attention. We don't want the network to pay too much attention to the words that aren't related to the current word being processed. So, to address these issues, Vaswani and his colleagues at Google Research published a transformer model, which is, in their paper, it was an encoder-decoder model. Next lecture, we will talk about transformer models that have evolved since then. We have encoder-only models. We have encoder-only models. We have decoder-only models. We have all sorts of different, we have layers. We have all sorts of different variations on transformers. But this basic transformer is the one that preceded it all. Okay? So this will be our vehicle for exploration. So this first step, to use this transformer, first step in this model is, let's first talk about tokenization, okay? Because how we actually input data into the model matters. and the model can't take in a symbol, right? That's not a thing. A model only takes in numbers, right? All these machine learning models only takes in numbers. So in one of the previous lectures, I believe it was an RNN lecture, we talked about one-hot encoding, where for each symbol we had a place in the vector that was related to that symbol, and so the vector associated with a certain symbol would be 0, 0, 0, 0, 1 for the place that corresponds to that symbol, and then 0, 0, 0, 0, right? That was one-hot encoding. So we're going to do something different. We can't really do that when our vocabulary size is in the hundreds of thousands, maybe soon to be millions, right? With our vocab, we are having one-hot encoding for having one-hot vectors that basically are a million long is absurd. So what we need to do is tokenization, right? We need to be able to break language up into little parts, into descriptive parts, but not too descriptive. Okay? Not under descriptive, not super abstract, not super descriptive. We have to find a good balance there. So as we described last time, we have this idea where we have multiple different tokenization methods. We have the character-based tokenization. This is primarily what we do with one-hot encoding. We break words up into characters, even spaces, and then each of the characters gets assigned a particular number. Bam, you put in the number into the machine learning network, and then it uses that. Okay? You have word-based encoding. You have where each word is assigned a particular number, and then we put that, and then that number gets fed to the machine learning network, and it uses that. Now, the benefit here is that the encoding space for this is pretty small, very small, right? It's only the number of characters. The encoding space for this is pretty large, right? It's just all the words, right? Which, I mean, there are, I forgot how many words there Merriam-Webster says exist in the English language. I think it's around on the order of 100,000, right? So if we have a number for each word, great. But then the issue becomes, what about things that aren't standard English? What about our names? Those don't necessarily exist in the English language, but we still need to represent them. Now, we could do a combination of this, of have a character, just have words and have characters for all the things, for all the words that don't exist in the word list. That's good. Or we can have a combination of things, right? So, for instance, the n-gram-based approach is the combination of things, is a combination of word-based. For instance, you want the word study to be tokenized, but it might be good to tokenize basically STUD as one thing, and then Y as another, EIOUS as another thing. Yeah, I don't know any other suffixes for studded. But it might be good to basically encode a word in a bunch of series of suffixes, because then we could combine different words, different suffixes, right? We compress the vocab space, but at the same time, we don't make it so small that we need to do every single particular vector. So, that's the sorry. So that's what's that's what tokenization is, right? So now, if we want to see tokenization in the real world, let's look at an actual example of tokenization. Last time we looked online for examples of tokenization, but now I want to actually show you tokenization in code. So what I'm going to do here is I'm going to cheat a little. Well, it's not cheating. I'm just going to download a pre-trained model, okay? A pre-trained transformer model. So a pre-trained model is simply a model that someone has spent the time and effort building and training on some corpus of data. They got a bunch of data from the internet. They had a transformer model. Google, Amazon, Facebook, everyone has their own LLMs. They build the transformer model, start off with some random seed, and then they train it on the internet. Okay? And then they get a particular model. And then they release that model for all of us to use because they're good altruists, right? So all I'm doing here is I'm loading a pre-trained model, and in this case, I'm loading a very tiny, not super smart pre-trained model. This is still GPT-2 because I want it to work on on a CPU. I don't have a GPU on that laptop. So all we are doing is basically we're asking the PyTorch to find this model and download it, and also download its tokenizer. Okay, so models, tokenizer, and so each model has a particular tokenization scheme. Okay, so all the tokenizer is doing, the tokenizer is simply a PyTorch object that looks at some tokenization scheme and converts text into tokens. Okay, so the actual tokenization scheme is basically like just a collection of tokens, right? The tokenizer is basically what breaks the words up into that collection of tokens. And you don't need a different tokenizer. You don't need a different program per model because why? They're all doing the same thing. They just have a list of tokens, and then a list of tokens, a list of associated numeric IDs, and then they're all just simply taking in the text and greedy decoding them into tokens. Does that make sense? So all I'm doing here is I'm loading a model. I'm putting it in evaluation mode. We talked about that. If a model, we don't want it in training mode because then we don't want to actually change the model, at least not currently. We'll talk about that more next time. So what we'll do is, I downloaded the same thing again. Okay, well, it doesn't have to be efficient. I downloaded the tokenizer again. So what we'll do is we'll simply take the tokenizer. We take a piece of sample text, the quick brown fox. We encode that text. We tell the tokenizer to encode that text into a series of input IDs. Or we could tell that tokenizer to tokenize that text into a series of tokens. And then we'll have a bunch of decoded tokens. And then if we encoded the string as a series of numeric numbers, we could also decode it based off the tokenizer. Okay? So if we do this, the quick brown fox, it gets tokenized as this. Okay? This special character G dot. This is basically just a random sample character that this particular model uses to denote a space. Okay, it's not the same across all models. There's no standards here. So this model knew it needed to denote this space as something. It chose this Unicode character because apparently maybe in its corpus it didn't see this Unicode character used anywhere else and it thought it's safe. So you could tokenize that sentence like so. Basically you have tokens, the G quick, G brown, G fox. Or you could take the IDs. You could first generate the IDs. These are the IDs that we would actually put into the model. And then we could decode them using the same tokenization scheme. Again, this right here is basically just a dictionary it downloads. So we could decode them using that dictionary and get the original words, hopefully, back. Yeah, please.
What's the point of using a special character for space and not just using space for the encoded character?
That's a good question. Why not just use space for the encoded character? In general, you don't want to just use space because it becomes hard to write code. Especially if you're looking for a particular token, then you just insert it in space, and it's unclear. You know, different compilers do weird things with spaces, right? So in general, you just put it as some character. And then, you know, if you could play around this. But for instance, one thing we discussed last time was that there is a difference between space word and then that word alone. So in this case, this with no space corresponds to the token ID 464. With the space, no, come on. Oh, because I restarted the computer. That's why it's taking a minute. Yep. With the space, it has a different token ID 383. You could play around with the tokenization. and you can play around with the different models as well. Okay? All right, so hopefully that makes sense. So a couple things to keep in mind. Tokens not equal to word. GPT-2, again, thank you. Like they use a special character to represent leading spaces. The number of tokens depends on how the text is broken into subwords. In this particular case, we're very lucky. I mean, each word in the text corresponds to a particular token. That's not necessarily always the case. And yeah. So now that we understand tokenization, let's talk about how inference works. How do we get the model to actually generate a piece of text? That's pretty much what we're interested in, right? That's what ChatGPT does. That's what all the modern language models do. That's their primary use case, to generate an actual string. So how do we generate an actual string? Well, let's look at what we get when we insert an input sequence into the model. So if we have, so again, we generated the model from the previous thing, and then if we enter in an input sequence, how is torch not defined? How is that possible? Why are you doing that? You know it's defined. You know it's defined. Okay, yeah, okay. No, that works, okay? So, let's say we have a bunch of input IDs. We encode the quick brown fox into the, numbers, the sequence of 4 numbers. And then this is the sequence of 4 numbers that we input, that we turn the brown fox into. And then all we're doing is that we're inputting this thing into the model, and the model object, remember, is defined like so. We're just downloading a particular LLM model from a pre-trained database, and then we get something out. We get a huge matrix out. This is the shape of what we get out. Okay, we get out what's called a logit, and this is the shape of the logit. It has 1 row, 4 columns, and 50,257 things next to it, right? So the question is, what are each of these things? What do each of these dimensions represent? So here's the key. Here's the idea. The first dimension represents batch size. Okay, batch size. I mean, you guys are well acquainted with batch sizes by now. So generally people like to process things in batches because, computing power is limited. So batch size is always sort of a parameter for the input and output of the models. Okay? Second option is the sequence length. The sequence length is the sequence length of the input. So over here, we had a sequence length that was 4 elements long. We get a sequence length that is 4 dimensions in Y. Right? The third dimension represents the vocab size. Represents the number of tokens in the vocabulary of this particular model. So in Distill GPT-2, Distill GPT-2 has a vocabulary size of 50,257. Okay? So what is this model? So what does this model tell us? Well, each logit at each place for some I represents the model's prediction of what token should come next after the ith token. Okay? So the logit of whatever, 1, 0, 0, that vector represents what should come after the first token. So the first token is the. This represents the probability space of what should come after that first token. Similarly, what should come after the second token, the third token. And this represents what should come after the very last token, which would be, in our case, 3. There are only 4 sequences, right? So what the model outputs is a vector for each token. That the vector in it contains a probability that corresponds to each particular token in the vocab. And so, the probability basically says how probable is this vocab item to come after this sequence item. Okay? So this particular vector, this will be just one vector, a one-dimensional vector. This vector gives us a probability, gives us a series of values, and each of those values corresponds to if this particular vocab element comes after the quick brown fox, comes after the word fox. Yeah, please, Oni.
So in our above example, the output would just be a vector with 50,257 elements?
Yeah, in the above example, yeah. So this would be, yeah, it would be a vector with that many elements. You might have to do a squeeze or unsqueeze to remove the one dimensions, the single element dimensions. But yeah, it becomes a vector. So we could do that actually. So generating a long sequence becomes a principle of starting off with some word, then putting it through the model. Then we get a distribution of all the particular characters. And next to this distribution, we have a number corresponding to, does that character come after the last token? And then we have a choice. We need to build more, right? We need to build a string. So what we'll do, at least in this initial stage, is we'll do what's called greedy decoding. Every time we get a particular probability distribution, we'll select the character that is most probable, okay? That the model says is most likely to come after the input that we've put in so far. So if we start off with the meaning of life is, the model could say that the next most probable token is 2. And then, so we'll put that into the input. The meaning of life is 2. Put that into the model. Then the model will give you a new probability curve. And then you have a bunch of different characters that it says are probable. B seems very probable. Live also might make sense, but we're going to go with B because it's the most probable. So we'll say the meaning of life is 2B, and then we'll put it into the model. And then we look for the characters that the model thinks could come after this value. It thinks understood could come after that. Very close behind, it thinks able could come after that. The meaning of life is to be understood. The meaning of life is to be able. The meaning of life is to be A. All of these things sound roughly correct, right? There doesn't seem to be anything wrong with any particular choice, which is probably why the probabilities of these choices are very close together. So we just choose one. We could choose the most probable. The meaning of life is to be understood, and we go on and on and on. Okay, that's how inference works. So that's the concept. But the beauty of this course is I'll give you an actual code example. So what we're doing here, oh man, okay. Actually, I could zoom. So what we're doing here, again, we have an input ID in code, and then we get a particular output. So all this function is doing is that it's generating a particular step. It's taking in the model, it's taking the tokenizer, it's taking an input text, and I'm taking in a device, CPU, because that's helpful. It makes it more generalizable. I'm sure many of you have found out that using a GPU is nice. So in this case, I'm leaving default at CPU to make things easier for you guys, but feel free to change it. So what all this model is doing is it's taking in the input, it's generating the input IDs, it's then putting those input IDs into the model, it's generating the output distribution, it's looking at the output distribution, looking at the output distribution after the last token, then it's putting the output distribution after the last token through a softmax function. Seems like a good idea, right? Softmax, when you get a probability distribution and you want to process it, you probably use softmax. So it's putting it through a softmax layer. Then we choose the top k elements. Let's say the top 10. This is just for illustrative purposes. Let's say see what the top 10 possible choices are. And then we decode these choices. Again, these are numbers. These probabilities, these indices are numbers, so we got to decode them. And then we choose the next token based off greedy decoding. We add it to the input text, and then we do the same thing over and over and over again. Okay, so this is how this function works, just so you know, and this is an example of using the function. So we start off with the text, the meaning of life is. We put this text into that generate step function. We put its tokenizer in. We put the text. We put the model in. We'll leave it working on CPU. And so we see meaning of life is. The next tokens are 2, not A. Meaning of life is 2. That sounds good. The meaning of life is not. I can imagine that's fine. The meaning of life is A. That's okay too. The meaning of life is that. That English is a little clunky, but I think that's fine. So we just choose the most probable thing, which is 2. And then we go on. We input in the meaning of life is 2 into the model, and then we see the most probable tokens. 2B is most probable. The meaning of life is 2B. That sounds good. The meaning of life is to live. Also sounds okay. The meaning of life is to say. That's a bit weird and conceptually, but I think that sounds okay English-wise. So you just choose the most probable token. The meaning of life is 2B. Again, we go down. We see the most probable. We see the most probable tokens. Understood, able, A. The meaning of life is 2B, A. Yep. The meaning of life is to be lived. That's fine. The meaning of life is to be found. That could work. And all of that, right? So we go on. We update the meaning of life is to be understood, and then we go on, move forward and forward and forward. Does that make sense? Okay. Does anyone want to know what this?
I really do want to know what.
Oh, you want it? That's what we. Yeah, it's a very unsatisfying answer, so I hate to spoil it for you. But yeah, if we run it, so new function just generate n tokens, and if we run it, if we run it for, I don't know, 20, it's just the meaning of life is to be understood as a whole, and to be understood as a whole, and to be understood as a whole. And yeah, so it was doing good. And then it sort of got stuck in a loop, which, happens with these simple models.
Does this model ever end sentences? Or
That's a good question. So does this model end sentences? So GPT-2 was a very unrefined model. It was a very unrefined model, and the biggest reason it was unrefined is because it didn't have any special characters, so it never really had any way to tell the user or tell the machine or render that I want to end here. Future models, and we'll talk about this more next time. More models, you'll see that current ChatGPT 3, 4, the llamas or whatever, are all trained with what's known as special tokens. So one of the special tokens is sort of the end of sentence EOS token. And then those models, when they're finished, they spit out the EOS token, and then that signals to sort of the wrapper that you should stop generating tokens. This was before all of that. So that's why it sort of gets stuck in a loop. Almost every language model, if they don't have the special tokens and they're like simple, they get stuck in a loop. Because you still want them to generate, right? If they don't say end, it'll just keep saying generate more, generate more, generate more. And at a certain point, I mean, you're just going to get into a pattern, right? It becomes a deterministic loop. OK. Fun? Seems good? Do we understand what inference is? I really want to drive home the point about what we're trying to do, what we're trying to infer. Because then when we talk about the transformer architecture, it becomes much more logical of what the inputs are and what the outputs are, and then we're just filling in sort of the in-between parts. Yeah? Oh, sorry, I didn't see you there. I'm not wearing my glasses, so that's why I'm not ignoring you.
So Microsoft looked at this answer and said, let's invest $1 billion in them. This
Yeah.
is something that